This is DesignSafe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hello, and welcome to another episode of DesignSafe Radio. I'm your host, Dan Zehner, and today we have a really excellent treat here with two graduate students from the UC Davis Centrifuge. We have Laura Luna and Jose Louis Caisapanta. Great to see you guys. It's always so fun to talk to graduate students because you haven't been jaded by the scientific academic world yet. You're still full of promise and optimism.
We are surviving. The good thing is that we're here.
Yeah, you guys are melting a bit down there this week, so I hope your AC gets fixed soon.
Okay.
Laura, you want to go ahead, go first, introduce yourself, and then Jose will continue with you.
Yeah, for sure. So yeah, my name is Laura Luna. I'm a third year PhD student here at Davis. And I'm working on the numerical modeling of cemented sands, which basically means we're just developing numerical tools to be able to predict how a cemented sand is going to behave during an earthquake.
Wonderful.
So that's what I'm doing.
Almost there. Well, 3 years out of how many in your program
3
are you
years.
aiming to?
We're hoping for one more, but I
Okay.
never want to say that because I'm scared I'm going to jinx it. So we'll see how it goes.
We'll knock on the wood for you here, hoping for
Thank
one more
you.
year. Great.
Yeah.
And how about you, Jose?
Hey, everyone. So my name is Jose Louis Caisapanta. I'm wrapping up my master's studies, but I will continue. I'll be here longer for a little bit more for my PhD. I'm from Ecuador, so where the seismic hazards are like pretty high. So I
Yes,
always
they are.
Yeah, not as much as Chile,
No.
but we have pretty big earthquakes. So I've always been interested in anything that is related to geotechnical earthquake engineering, such as site response and liquefaction. So that's why I was really interested to come to the west coast of US. So yeah, here we are.
So one of the interesting things that you guys are well into your graduate studies. We may have some undergrads listening, or maybe the REU students. I know they love to listen to the podcast. So hey, out there. For those who are unfamiliar with centrifuge research and testing, can you describe the project you're working on, how you use the centrifuge, and then what is it like using a 9-meter diameter piece of equipment you got behind you, Laura?
Maybe I'll let Jose Luis go first on this one.
Sounds good.
Good. So let's try to make it simple. Let's think about this container that is just behind me, right? And we can just build a 1 meter tall embankment, which is just a solid structure. And then the centrifuge is just a scale test, right? So we speed up the centrifuge up to, let's see, 50G. And then that 1 meter embankment at centrifuge scale, which is called normally prototype scale, it will be representing a 50-meter tall embankment. So once we are at that G level, then we can induce some deformations to the embankment and evaluate it based, like, I don't know, simulate some earthquakes by using the shake table that we have in our 9-meter and also 1-meter centrifuge. There's a really interesting project right now that is being done by a postdoc. He will induce some crack deformations by just at the bottom of the embankment. He will just rub it down a little bit, and then he will track the erosion.
Oh.
So, interesting. This is just a problem where, I don't know, if you have an embankment that is built in a fault, this can be induced by a fault movement during an earthquake. So these kind of convoluted projects that are really interesting, they can be done here in the centrifuge, and we don't need to go to the field and try to simulate some liquefaction by blasting the surface, which is not the same mechanism. And also, we don't need to wait up until an earthquake happens. I don't know, who knows what will happen in 10 or 20 years. We have everything in our lab. So that's why I think the centrifuge is a really great tool for us as civil engineers, because also it's not useful for geotechs. There's so many structural engineers that will try to build up their structures, and we'll see the response during earthquakes. So this is open for everyone. So, and you guys might be wondering how we track and how we try to evaluate the responses. Here you'll see, well, you won't see anything below the ground surface, but there's a bunch of sensors. This is the test that I was involved during my master's. I was helping a postdoc. So down the soil, we have some accelerometers to track accelerations in depth. We have also pore pressure transducers. Bender elements will help us out to track shear wave velocities to see the change of the stiffness of the soil before and after the shake. And then we also have linear potentiometers to track deformations, which are the ones that you see this huge beam here. So there's like a little sensor in here with a plate. If that plate goes down, that linear potentiometer will track how much it moved during and after the earthquake. So now we're trying to implement some kind of high-speed cameras, which look really cool. So how we use those high-speed cameras, you'll see that we have also soil markers at the ground surface, and also the structures little structure that we have, like they have like a square grid like camera tracker. So we track some points using an image analyzer software. And, yeah, that's pretty cool, right? So then we can stop using those kind of beams that will kind of like stop your clear view of your test, and just use the high-speed cameras during our test. So just to wrap up a little bit, our project was related about a biomediated ground improvement. I work with Jason DeJong. So we're trying to evaluate how the structure is responding by using this MICP sand, by inducing also, now we're using ground motions, and see how the structure responds, and the changes on how tall or short the structure is, how this will affect the final response of the structures.
Wow.
So it's great. We did this like probably 1 month ago. So it's really relieving that now we're done. We're just playing around with the data. So it's been great.
Yeah. And am I seeing water on the surface there? Are you looking at really saturated soil?
Yeah. So usually if we want the sand to liquefy, it has to be saturated. So also that's why we would try to have like a broad view of the lab. We're just not focusing in earthquakes. We know that in natural hazards, right now, I think some RU students are working on trying to see if we can evaluate permafrost. So we are freezing soil right now, and they are using the 1 meter centrifuge, and they try to see in the future projects, we can see how a structure or any kind of, I don't know, like soil structure, how will respond during the melting process of the permafrost. So yeah, it's great. So this tool helps a lot and gives like some different kind of projects to have like a broader view. And yeah, it's been great for now until now. Yeah.
That's really cool. And it reminds me of last year at the AGU conference, the American Geophysical Union. I had ended up in a meeting with a bunch of permafrost scientists. Like they were all together in a bar, and a lot of fun. The people who research permafrost. So maybe we can get some of those field researchers into the lab on the 1 meter centrifuge.
Yeah. So the goal, I think, is try to open to more people to come to our facility, since our facility is not only fixed for UC Davis students. Like it's open for any university that is just interested in doing research on the centrifuge. So that's why we don't have that permafrost problem here in California, but back in Canada, they probably will have that. So we're trying to open like more spots to more universities to come and have this experience.
Yeah, amazing. Thanks for sharing, Jose. Laura, can you tell us a bit about your project?
Yeah, for sure. So my project is about developing computer models that can predict how the cemented sands are going to behave during an earthquake. And so it actually works really well with the project that Jose Luis was talking about, where they were working on biocemented foundations. Because as I'm working on the model, I use lab data like direct simple shear and triaxial data to sort of make sure that the model matches the experiments that we have. But those are not a full geotechnical system. That's not a building. And it's not like I can just go somewhere and buy a cement and make an earthquake happen in the field in reality. Maybe if I had a lot of money. But so the centrifuge is sort of a great way of collecting data on how that would happen. And so you have a scaled model that then, by nature of spinning it, is going to have realistic stresses. And then when you shake it, you can start to study what would happen during an earthquake. And then I can grab all of the data from the sensors that Jose Luis mentioned, like the accelerometers and the pore water pressures, and the settlements. And then I can make my own computer model and see how they compare, and see if it matches really well, or if there are any area for improvements for the model. And in general, it can sort of improve the confidence that we have that the model can predict real life situations. And so for me, it's great that I was able to get involved in the planning of the centrifuge model, because it looks really big, but once you start placing all of the sensors, you can see all of the cables. And so it becomes a bit of a logistical challenge to be like, how are we going to fit everything in? And then when you actually start building things, so I had the chance to help a little bit with the construction of the model. And so you're kind of raining sand on the model by air pluviation, we call it. And then you have to measure everything. And so there's a lot of details that I think until you go through it and sort of go through the building process, you don't understand the level of complexity. So it's truly such a great opportunity to get involved with like centrifuge models. And also that I really enjoy the teamwork. So the opportunity to work with other grad students, with undergraduate students, and with the staff at the CGN, and obviously the professors. It's sort of like great minds coming together for a good project. So it's a lot of fun.
You made a couple of really good points that I want to highlight, of how, especially getting into experimental science, there's no substitute for being involved in the real thing and actually building it, because you think, oh, it's no big deal, you just put things in the box and you put the sand in there, you put some sensors. Like, no, it's really complex.
It is. It's pretty hard.
Like every single tape that we had to put, and making sure, like, where is this cable gonna go? Like, everything looks a lot easier in paper.
Right. And how do you make sure that the zip ties don't break when it's subject to 50G? And make sure that when things start moving around, that all of the screws are actually torqued down so a camera doesn't go flying off into space. And
the cables too, because when the arm pops up, there's going to be tension on the cable, so you don't want to be breaking your sensors.
Exactly. Like, how much slack do you leave in the cables, and where does that slack sit so that it can swing and not pinch things? And a lot to take into account, that especially as engineers, we kind of take for granted that it's just going to happen. But when you actually go out and build it, it's like, there's a lot more of putting it together and taking it apart, and what order do things go, and that's really important. So it's valuable experience there that you're getting.
Yes, for sure.
Thanks for listening to today's episode of DesignSafe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zehner. We'll see you in the next episode. Until then, stay resilient.